Hi, this video covers our second draft of the vector-based Q. We're going to solve this wraparound problem, and as we'll see at the end of the video, we're going to get closer, but we're not quite finished. There's going to be one more draft after this one. So let's quickly recap the issue in the previous video. We had this scenario with a vector that has capacity 4. It has 4 elements that could store Q elements. My size of the Q was always 1 or 2. I always had 1 or 2 elements in use. But the vector drifted out of bounds. The elements I was using kept using higher and higher indices until we got past index number 3, and then it would crash because we would go array out of bounds. And the problem is that the first 3 elements are kind of wasted. The way that this data structure is using elements is they get to be used once, and then they're kind of burned up and never used again. And that's kind of wasteful. It just churns through these elements at the beginning and doesn't reuse them. In general, if I is an index of an element, it's wasted when I is less than front. So in the sketch here, front is 3, and every index less than 3 is used up and burned up and will never be used again. It's just wasted. So the solution is, instead of treating elements that way, we're going to kind of recycle them. And when we get to the end of the vector, we're going to wrap around, in a sense, and start from the front again. So instead of just treating index 0 as burned up and unusable, when we want to enqueue another element after the 4, there's no space to the right of 4, so instead we'll start over at the left. And then from there we'll keep enqueuing rightward. So if we were to do that and we were to enqueue the 5, it would go at index number 0. Now this will involve modulo arithmetic, so we're going to do a quick review of modulo arithmetic. In most programming languages you use the percent operator to do that. So n%d says you take number n and do divide by d for divisor, and get the remainder. Mathematicians pronounce this n mod d, n modulo d, or n mod d for short. It's the remainder of n divided by d. Now, the way that remainders work is, as n increases, the number we're dividing by, n mod d wraps around. So n mod d will get bigger and bigger and bigger until it gets up to d minus 1. Then the next increment gives us 0 again. So let's see how that works. 0 mod 4 gives us 0. That's 0 divided by 4. 0 divided by 4 in long division is 0 with a remainder of 0. And this 0 is the remainder. 1 mod 4 means 1 divided by 4. 1 divided by 4 is 0 with a remainder of 1. So that expression gives us 1. And as we increase n, the number we're dividing by, we get 2. Then we get 3. Then 0 again. That's the important thing. 4 divided by 4 is 1 with a remainder of 0, so we get 0 out of that expression. Then it keeps going 1, 2, 3, and then 0 again. You can envision this as going clockwise around a circle like this. So I labeled these 0, 1, 2, 3. If I count off my n, increasing from 0, 1, 2, 3, 4, 5, 6, 7, 8, every time I increase, we go clockwise 90 degrees, one quadrant of this circle. So 0 mod 4 gives 0. 1 mod 4 gives 1. I get 2, 3, 0. 1, 2, 3, 0. And it spins around like that. This is also reminiscent of the way that the hours work on an analog clock. Okay, so what we're going to do is use modulo arithmetic to help us with this calculation of indices in our Q. So let's say I is a valid index, meaning it's between 0 and the vector size minus 1 inclusive. And I want to increase index I by k, and I want to do this wraparound thing where if I go off to the right past the last valid index, I wrap around back to 0 again. So what I want to do is compute index I plus k with this wraparound function. Now, I plus k might be out of bounds. Remember when I did that front plus size thing, I got 5 that was out of bounds. And the way that we solve that is to do I plus k modulo vector dot size. And the way that modulo works is this modulo vector dot size will certainly be in bounds. That will always be between 0 and vector size minus 1 inclusive. Okay, so let's see how to apply that. What we're going to do is go back and revise our first draft code, and anytime I increase an index in the vector, I'm going to do that increase mod vector dot size. The front operation is the same as before. We just return the vector at index front. Again, we should really have a if size is 0, throw an exception check, but we're going to deal with that detail later. DQ is a little bit different now. So earlier we just said front plus plus, size minus minus. What we're going to do now is say we're going to increase front by 1. We're increasing an index, so we do the mod vector size thing. So front equals front plus 1 modulo vector dot size. Most of the time that will just increase front by 1. In this modulo vector size will have no effect. But in the one case where front is 5 to begin with, then 5 plus 1 makes 6. 6 mod 6 in this example, my vector has capacity 6, so 6 mod 6 is 0, and in that case front would be computed as index 0, which is what we want. Size minus minus keeps the size accurate as before. And NQ needs the same kind of change. I broke this calculation of the index onto its own line to make this clearer. So I is the index where we're going to NQX, meaning I is the back of the queue, so we do front plus size. Most of the time that's going to be a valid index, but we do front plus size mod vector dot size. Most of the time front plus size is already valid, but in the event that front plus size is greater than 5, then the mod vector dot size does the wraparound for us and we move back to number 0. So once I calculate that index, vector of I is equal to x, and we do size plus plus to keep the size accurate. This will solve that wear out problem. Once we NQ past the end of the vector, we'll wrap around and start using the low indices starting from 0, and we'll be able to keep NQing and DQing as long as you want to, as long as we never overflow the vector. Let's just look at an example of this. So starting from an empty vector, if we NQ3, if you go through this arithmetic, first plus size would be 0 plus 0, mod 4 is still 0, so we NQ at index 3. And until we get to the end, this modulo vector size won't really have an effect on anything. So if I NQ4, that will go at index 1, NQ5 goes at index number 2. Now let's say I DQ, then we'll say first is first plus 1 mod vector size, so that's number 1, so that just eliminates the element at index 0, front is now 1. If I NQ6, first plus size would be 1 plus 2, mod 4 is still 3, so we NQ at index 3 at the back. Okay, now is where the wraparound happens. If I NQ7, first plus size mod vector dot size is 1 plus 3. 1 plus 3 is 4. 4 mod 4 is 0. So 7 will get NQ'd at index 0, and that's what we want. So this queue, I would call it, it's kind of flipped right now. The front is at index 1, but the back is at index 0, and that's allowed. So there's some good news and some bad news at this point. The good news is the elements wrap around like we want, so the drift problem is solved. In this scenario, the indices in use drift up higher and higher until we get to the end of the vector at index number 3, and then we wrap around to index number 0 instead of going out of bounds. So that's a good thing. We can alternate NQ, DQ, NQ, DQ, and we'll just keep looping around the same elements of the vector indefinitely. So we've matched the linked list-based queue where NQ, DQ doesn't wear out our vector-based queue. But the bad news is we're not quite done. There's still a problem where the vector-based queue can overflow. In this example, the vector has size 4, so the queue has capacity 4. We can never store more than 4 elements in this queue. And our vector-based queue has a limited capacity, therefore. But the linked list-based queue doesn't have that. You can make a linked list-based queue as long as you want. So in the next video, we're going to solve this one last problem of the limited capacity. We're going to make it so that our vector-based queue can grow its capacity so that the vector-based queue can hold as many elements as we want.